As you know, I've been going on and on about motion with constant acceleration. And I started out that description with a number line, which you've probably been thinking of as the x-axis. And that makes sense because I'm going to move along. I define the origin of my coordinate system. That direction's positive. I've got my number line here. And I move this way and that way. And my goal was to describe the universe in the context of my position, which leads me to displacement, which leads me to velocity, which leads me to acceleration. So my description of the universe becomes more and more sophisticated over time. But here's the thing. My universe, the universe that I would like to describe, is not one-dimensional. We don't all live on the same x-axis. We're not one-dimensional, but in fact three-dimensional. Not only do we have an x-axis, but also a y-axis and a z-axis. And if I'm to describe my universe properly, I'm going to need to describe motion in more than one dimension. There's a really simple example of that, and in fact one that we'll solve. Here I have my marker here. If I throw it from my right hand to my left hand, it follows a curved, arcing path through space and time that is much more complicated than the problems that I've solved so far. So far, I've solved a problem of a car skids to a stop. That is linear motion in a straight line. I solved the problem of the engagement ring thrown up to the window, and that is a one-dimensional problem as it rises and falls. But when I throw the marker, right hand to left hand, it rises and falls under the influence of gravity. It moves from your perspective, from left to right, along the x-axis, but at the same time, while it's simultaneously doing that, it rises and falls along the y-axis, making a path through space and time that you might suspect is a parabola. By the way, if you think it's a parabola, you're completely right about that. In a little bit, probably tomorrow, I'm going to prove that it is. But for now, I just want to appreciate the fact that that motion seems to be a great deal more complex. And so you worry, oh no, physics is going to get much harder now. But it turns out it's not. Because I have a special way of treating motion in higher dimensions that makes it very, very, very simple to do. And it has everything to do with these new mathematical objects we've learned about called vectors. The very first vector that you know about is the vector displacement. I have an equation for it. The vector displacement delta x is equal to the final position minus the initial position. When I first introduced that, it just seems like subtraction. But then you discover that based on a coordinate system that I choose, that the displacement can be positive or the displacement can be negative. What does it mean? Well, positive displacement means I displace in the positive direction. Negative displacement means I displace in the negative direction. And so displacement is a new kind of number. It's a vector quantity. It's an amount, it's a quantity that has an amount that we call its magnitude and also has a direction to it, a vector quantity. Well, if I write it like this, it makes perfect sense to me because subtraction is not difficult to do. I know that the positions in my coordinate system could be positive or negative, and if I just do the math carefully, it works out. Positive displacements, positive direction, negative displacements, negative direction. For example, if I had calculated this, it might work out whatever the positions are. It's not like I'm not fleshing out the example here, but imagine it works out to be 5 meters. When I write that as the answer, you, the student, know that because displacement is a vector quantity, that what I mean by that is 5 meters in the positive direction. I would like to suggest that there's another way that I could express that. I could, instead of writing plus 5 meters, I could draw an arrow on the board that points in the direction of the displacement. So not surprisingly, I've drawn it, as I would conventionally, in the direction of the positive x-axis, and just right above it, 5 meters. Arrows are excellent for describing vector quantities, because a vector quantity has an amount and also has a direction. This arrow has a length and also points in a direction. Now you say, well, it's a 5 meter long arrow. Consider that I'm 2 meters tall. An arrow drawn 5 meters long would be enormous. You know that if you put a ruler up here, that arrow is not 5 meters. What I mean is that that arrow represents 5 meters. So that if I wanted to, in this new world of arrows that I have, if I wanted to describe a displacement that was twice the displacement, that would be positive 10 meters, would be twice the displacement. What I would do is I would draw an arrow that was in the positive direction, and was twice as long as the original arrow. So by scale, I have an arrow that represents a vector displacement of 5 meters and an arrow that represents a vector displacement of 10 meters. Now it gets fancy, because if I draw an arrow that's the same length as my 5-meter displacement, but I draw it in the opposite direction, then this arrow representing this displacement, I'm just going to label it with 5 meters, as I did for the positive 5-meter displacement, but the arrow points in the negative direction. So the arrow gives me the direction. So now I could just redo all of the physics that I've done, where my positions, displacements, velocities, and accelerations are all arrows. Now, it'd be perfectly correct if you were sitting there thinking, nah, I like it the way we're doing already, because you just subtract. And subtraction is easy to do. I don't need to be messing around with these arrows. But the arrows, it turns out, are a great advantage to me whenever I decide that instead of solving problems in 1 dimension, I'd like to solve problems in higher dimensions, 2 dimensions, 3 dimensions, or more, as it happens when your physics gets really fancy. But for the moment, let me consider 2-dimensional motion. That makes sense, because the problem that I said that I wanted to solve was the problem of projectile motion, my marker flying through the air from hand to hand, where it goes sideways and up and down. 2-dimensional motion. Well, now, if I want to describe 2-dimensional motion, and I say the displacement is 5 meters, what should I say for the direction? If my motion is 2-dimensional, I can't say plus or minus to indicate direction. Plus or minus isn't good enough. So what I do is I draw a displacement as an arrow. Notice that this arrow that I just drew, a blank arrow on the board, this arrow does not point along what we would, all conventionally agree is the x-axis. It does not point along the y-axis. It's kind of both. A little bit scary, because now I've broken off the x-axis, made the universe a bigger place. This is now my displacement vector in 2 dimensions. I can't call it delta x anymore, stressing that I can call things in physics anything I want. But calling that vector delta x is a really bad idea, because delta x is like x-axis, right? We call it delta x because it reminds us all of the x-axis in our coordinate system, our traditional coordinate system. I can't call it delta x. I wouldn't want to call it delta y, because while it does go upward somewhat, it's not all upward. It's kind of a combination of upward and sideways. What shall I call it? What would be a good name? What do you think? What's that? We see delta z is also a coordinate direction. Here I chose to go in 2 dimensions only. So that brings me x and y. As you learned in math class, now you also get z in there. I don't want to mess with delta z. That's also a potential coordinate direction. Come on, what do you think? Anyone? That's not bad. That's not bad, because u isn't busy doing a lot of it in physics, so it wouldn't be a bad choice. There is an actual answer, and I think maybe it might not surprise you, depending on how your math teachers talk about this sort of thing. I choose to call it delta r. Delta r is the displacement in 2 dimensions, and by the way, if I added the z direction there to it, I'd still call it delta r, except it would be 3-dimensional. If I added a 4th dimension, it'd be 4th dimension. What? If I added 11 dimensions, I'd still call it delta r, because delta r is the total displacement in space. So now the thing's gotten a bit complicated, and this is the part where you imagine I could be in trouble, because just as the projectile, as it goes to my marker as a projectile, goes from my right hand to my left hand by going along the x-axis while also moving along the y-axis simultaneously, this displacement delta r has a part that is directed along the x-axis that is delta x. That is, there's an aspect of delta r that is along the x-axis. There's also an aspect of delta r that is along the y-axis. I'll call that delta y. This displacement has 2 parts to it. It's got a sideways part, it's got an upways part. Here's the amazing. The displacement delta x and the displacement delta y are the parts of the total displacement. And it turns out to be a beautiful aspect of the nature of our universe, that when I'm describing motion in 2 dimensions, like the motion of the projectile, I can describe it as motion along the x-axis, in this case the displacement delta x, and motion along the y-axis, delta y, independently. That is, I can take the two-dimensional problem of delta r and break it down into two separate one-dimensional problems, delta x and delta y. And the reason why I like that is because I know how to solve delta x problems, don't I? To a reasonable degree. We're still solving problems and learning about how to apply kinematic equations to the solution of problems. But by and large, I know how to solve problems in one dimension. So I'm going to take a two-dimensional problem and I'm going to find the one-dimensional parts of the problem. The two-dimensional problem is delta r. The one-dimensional problems are delta x and delta y. That's what I'm going to do. Well, then a big question comes up. If I know what delta r is, if I have that arrow that is delta r in two dimensions, how do I find the parts? That's the big question that I have. How do I find the parts of a vector when I know the vector arrow in 2 or 3 dimensions or higher? The parts of a vector have a name. The parts of a vector are called that vector's components. The components of a vector are its x and y parts. The components of a vector are its x and y parts. So here's my plan. I've got problems in 2 dimensions, like projectile motion, that I want to solve. I realize that I can solve them by dividing them into 2 parts. A y-axis part and an x-axis part, a horizontal part and a vertical part. But in order to do that, I need to be able to find the parts. And that may be a tricky thing to do, finding the parts of a vector, the components of a vector. Well, maybe it's not as bad as it seems, because if this is delta y over here that I've drawn, the part of the vector that is the upward part, imagine that I grab that part and I shift it over to this side of the diagram. I just take that bit, which is delta y, and draw it over here. It would certainly be delta y. And when I do that, a very special and powerful thing happens. When I move that delta y over to this side of the diagram, my diagram for the vector displacement delta r now looks like a right triangle. And human beings love right triangles. We've been loving right triangles the entire time. Right triangles are fantastic because they have mathematical properties. And all of human science and engineering is based on those very simple mathematical properties. Everyone loves it. Everyone recognizes it on sight. That for this diagram I've drawn here, delta r squared is equal to delta x squared plus delta y squared. The Pythagorean theorem. The Pythagorean theorem gives me a relationship among the sides of a right triangle. What it tells me is that delta x and delta y are in fact related to delta r. I want to find those parts, so it's nice to know that they're related. There is some mathematical relationship. Unfortunately, the Pythagorean theorem is not going to do it. The Pythagorean theorem is not enough. What I need is more about the relationship between the sides of right triangles and the interior angle. There is an entire branch of mathematics dedicated to right triangles, their sides, angles, and the relationship. That branch of mathematics, of course, is called trigonometry. You've all studied trigonometry. Now, that might produce a collective groan, because when you first learn about trigonometry as a mathematics student, there's all kinds of details. It goes on and on and on, doesn't it? All kinds of proofs with secants and cotangents and stuff and messing around with those things. There are the law of sines and law of cosines and all of these sort of algebraic things that happen in it. It's very, very sophisticated. But good news for you. Trigonometry applied to physics, which, by the way, is the point of trigonometry. That's why trigonometry exists. The application of trigonometry to physics is actually quite simple. So simple, in fact, that it's only going to take a few minutes for me to explain how it applies. So really quickly, I'm going to stop being so physicsy about what I'm saying. I'm going to swap to being mathematical. And I'm going to talk just about right triangles and the properties that they have. I'm going to draw a right triangle here. I know that it's a right triangle because it's a triangle where one of the interior angles is 90 degrees. I think we're all aware that the sides of a right triangle have names. In particular, I think everyone remembers that the long side of the right triangle is called the hypotenuse. That's the hypotenuse of my right triangle, and I need an interior angle. I'm going to call that interior angle theta. While I know that you learned all about trigonometry, for some reason I find that students at this point are not familiar with Greek letters like theta. Have we all seen a theta before? Some yes, some no. This is the Greek letter theta. Typically in physics, we use the early Greek letters in the Greek alphabet to designate angles. Alpha, beta, gamma, theta. They're commonly used in physics to describe angles. So there's an interior angle. Here's the important skill. Here's the one that matters. And by the way, as a practicing physicist, this is a skill that I use all the time. When I see a right triangle, I need to be able to look at it and know which side of the triangle is the adjacent side. That is, which one is actually named adjacent. I could name them anything that I want, but they're named by convention. So which side is the adjacent side? It turns out the side that is roughly oriented along the x-axis here in my diagram is the adjacent side. It's called that because it is adjacent to the angle. It lives next door to the angle. In your math classes, a tragic thing might have happened. You might have been taught to associate the adjacent side of triangles explicitly with the x-axis. That is not true and actually dangerous thinking. I need to be able to look at a right triangle in any orientation in space. However, I turn it around, twist it, look at it upside down, hang from a tree, whatever, and be able to look at a right triangle and identify which side of the right triangle is the adjacent side. In this case, it is that side, the side adjacent to the angle. The other one is called the opposite side. Now, the observation that we make in trigonometry is that for a right triangle with a given interior angle, let's say 30 degrees, and by the way, if I choose that angle theta is 30 degrees, then clearly the other angle is 60 degrees, because the sum total of angles inside of a triangle is 180 degrees. But what trigonometry does for me is make the realization that if I have a triangle whose interior angle is 30 degrees, then the ratios of the sides of the triangle are constant. That is, if I draw a 30 degree right triangle on the head of a pin, and I draw a 30 degree right triangle on a piece of paper, and I draw a 30 degree right triangle on the football field, the side lengths of all those triangles are very, very different, but the ratios of the sides of the triangles are exactly the same. It's a property of right triangles. So if I compute the ratios of the sides, that is one side divided by the other. For example, the adjacent side of the triangle divided by the hypotenuse of the triangle, that number is going to be the same no matter what the scale of the triangle for a given angle. So if it's 30 degrees, that ratio is the same no matter how big you make the triangle or how small. And so we give it a name. It's called the cosine of that triangle for a given angle, theta. That's the name that it was given. It was given cosine. Could have called it Sam, but they chose to call it cosine. Probably because they had an idea that people were beginning to understand it, so they wanted to make it more complicated. Give it a funky name. It's called the cosine. But that's not the only ratio that there is. I could also take the opposite side of the triangle, divide that by the hypotenuse as well. That's a thing that I could do. That ratio is called the sine of the angle. That ratio is called the sine of the angle. And I could take the opposite side and divide it by the adjacent side. That is called the tangent of the angle. I know it's a little funny that I write tangent different than I write sine and cosine. It's a habit that it's impossible for me to break. I just happen to do that. Cosine, sine, and tangent. The relationship among the sides of the right... Wait a second, Scheidly. This is starting to sound like math class. I don't know what the hell we're doing anymore. Let me tell you. Let me reiterate. I would like to understand motion in higher dimensions. Motion like the projectile motion of the marker from one hand to the other. When going from one hand to the other, the marker goes along the x-axis, but it also goes along the y-axis. That's the motion I would like to understand. And I reason out that if I could find the x-axis part of that motion, and if I could find the y-axis part of that motion, then I can solve those two motions separately and not worry about the more complicated motion. So what I'm trying to do is I'm trying to find the parts. Why do we need parts? Well, imagine this. Slim plays football, I guess. And you know Slim plays quarterback. Slim throws the football. When he throws the football with an initial velocity v0 that is not horizontal. It is not vertical. It is both simultaneously. I express that velocity as a vector in two-dimensional space, an arrow that's as long as Slim can throw and that points in the direction that Slim throws. And then the football does its complicated motion after that. What I want to do is I want to find the horizontal part of the motion. I want to find the vertical part of the motion. Well, let me draw them in. That's the horizontal part of the velocity. Makes sense, I'll call it Vx. And that is the angle at which Slim throws it relative to the horizontal. Now, I want to find out what Vx is. I'll use a little trigonometry. Because I know what V0 is, and V0 is the hypotenuse, and I know that Vx is the adjacent side, and that's the key skill. To be able to look at it and say, that is the adjacent side. That is the key skill. I realize that it is the cosine function that relates the adjacent and the hypotenuse. It's the cosine function. Doing a little bit of algebra over here, I see that the adjacent side can be found by taking the hypotenuse times the cosine of theta. And so, Vx, which I would call the x component of the velocity, the horizontal part, the x part of the velocity, is equal to V0 times the cosine of theta. That's the skill that I needed. Because if I'm going to solve it in parts, I need to be able to find the parts so I can get started. So the horizontal part of the motion is V0 cosine theta. What about the vertical part? Because to a certain extent he's throwing it horizontally, but also to a certain extent he's throwing it vertically. What about Vy? Well, I've already used cosine. The other component is found using sine. Look here. Vy is the adjacent component. Is the opposite component, pardon me. It's the opposite component, and I can find the opposite component by taking the hypotenuse and multiplying by the sine of theta. And so Vy is equal to V0 times the sine of theta. And so I have the two components of the velocity. Vx is equal to V0 times the cosine of theta. That's the horizontal component of the velocity. And Vy is equal to V0 times the sine of theta. That's the vertical component of the velocity. And now I found the parts. Now I can use that x velocity to go ahead and solve an x-axis one-dimensional motion problem. And I already know how to solve those problems. And I can take the y velocity and I can solve a y-axis one-dimensional motion problem. In the case of a football, that problem is going to be a free fall problem. And so I can solve all the way to the end. And when I solve all the way to the end of the motion, it gets caught by the receiver. When I solve all the way to the end of the motion, what I've got at the end is parts. Once I get to the end of the problem, I need a way to put the parts back together again. Because in order to solve the problem, I took the problem, I broke it into parts. And then I solve it. And at the end, I have to put the parts back together again. Well, theorem of Pythagoras. The velocity is equal to the square root of the x velocity squared plus the y velocity squared. Now it's really telling there that I say velocity. You have to be careful. This is the magnitude of the velocity, the amount of velocity. Velocity is a vector. It has a magnitude and a direction associated with it. By taking the sum of the square roots of the components of the velocity, I've found the magnitude of the velocity. I need its direction. But when I'm talking about a vector in 2 dimensions, I can't just say plus or minus. That doesn't mean anything. In order to describe the direction of the motion in 2 dimensions, I'm going to need an angle. And in order to get the angle, I use my third trigonometric definition here. That the tangent of theta is the opposite divided by the adjacent. But I'm going to use it in a very specific way. That the angle is equal to the inverse tangent of the y velocity divided by the x velocity. Inverse tangent, what the heck? Sure. What tangent does is say, you tell me the angle, and I'll tell you what the ratio of the opposite side over the adjacent side is. That's what tangent does. What inverse tangent does is says, you give me the ratio, I'll tell you the angle. They are inverse functions, tangent of theta and inverse tangent. They are inverse functions of each other. So I tell you what the ratio of the sides are, the opposite side, which is Vy, divided by the adjacent side, which is Vx, inverse tangent, and it tells me the angle. So my strategy will be this. When I want to solve a problem that is 2-dimensional, I will break that 2-dimensional problem down into 2 separate 1-dimensional problems. I'll then solve those 1-dimensional problems because that's a thing that I know how to do. And then when I get to the end of that solution, I'll bring that x-axis solution and that y-axis solution together and reform the 2-dimensional answer.